Today we continue with mass moment of inertia. Just to review, last time we looked at the definition of a mass moment of inertia. We said that we can find it by integration, integral of r squared dm, where dm is a small increment of mass and r is the distance away from the axis of interest to us. We saw that for most cases we don't need to do integration because common shapes have tabulated values. For example, here's the cylinder. We can see the mass moment inertia tabulated for the three axes that are shown here, all of which pass through the center of mass G. Sometimes, though, we said we need to find the mass moment inertia about an axis that doesn't pass through the center of mass G, and for that we're going to use the parallel axis theorem. So an example that we looked at last time would be, suppose we want to find the mass moment inertia about the x prime axis, and in that case we do use the parallel axis theorem, which is that we can take the mass moment inertia about the axis through the center of mass, which we'll call I sub x, and any other axis parallel to that, we can find the mass moment inertia about that axis by adding the quantity md squared, where d is the distance between the two axes. And again, the smallest value that's going to be possible is going to be for the one that passes through the center of mass G. So on the right side of the equation, that first one has to be the one that passes through the center of mass. For compound bodies, we said we can add mass moments of inertia together as long as they are about the same axis. So we have to use the parallel axis theorem usually to find the value for each component and then add them together. Now, one thing that we come across in this class is that sometimes we'll need to find where the center of mass is located for a compound body. For example, this pendulum here, which is made up of a thin rod and we'll say either a sphere or a cylinder at the bottom. And to do that, what you'll do is to find the distance away from some fixed datum. In this case, the top of the rod would make where the axis is shown would make a good datum. And so we look at the distance to the center of mass of each one of the parts. Then we multiply that distance by the individual part's mass, and then sum those together and divide by the total mass. In other words, it's an equation here. If I'm measuring from the top, then the quantity y bar down to the center of mass of the entire pendulum, I would find by taking the y bar of the thin rod, multiplying by its mass, adding to that y bar of the sphere at the bottom times its mass, adding those together and then dividing by the total mass, and that would give me the value of y bar. So it's like a weighted average of how far away each center of mass of each of the individual components is. So that kind of wraps us up for mass moment of inertia. But now that we know how to do that, we can apply that to the equation that we talked about earlier, that for rotation of a rigid body, that the sum of the moments about the center of mass is equal to the mass moment inertia about an axis through the center of mass times the angular acceleration. We'll also see we can do it about different points as well with some adjustments to this. But now that we know how to calculate the mass moments of inertia, now we can move on to the class of problems, the kinetics of rigid bodies that are undergoing either rotation or general plane motion.